Hello and welcome to this video lecture on novel aircraft configurations. My name is Carmine Varriale and I am Assistant Professor of Flight Mechanics at the section of Flight Performance and Propulsion here at the Faculty of Aerospace Engineering of the TU Delft. In this video, we're going to look at the unique aerodynamic properties of the boxwing, and we're going to try to understand why it is interesting to consider a boxwing aircraft as a potential solution towards a more sustainable aviation in the future. First of all, what is a boxwing and why is it called like that? A boxwing is a closed wing system consisting of two main wings connected to each other by side panels or side wings at the tip. It is called like this because if you look at it from the front or from the back, the profile of the wing looks like a box, or more in general like a closed curve or polygon. Depending on the particular application and category of the aircraft, there are many possible designs for the geometry of a boxwing. And the same is true about the possibilities to integrate it with a fuselage and vertical tail in order to make a proper aircraft configuration. The examples that you see in the pictures have actually already flown in the real world for light and ultralight applications, but there are many more that are currently being studied in research. For flight in transonic conditions, which is the current standard for transport jets, all wings of the boxwing have to be given a certain sweep angle and, as a consequence, a significant horizontal distance, which we call stagger. This particular aircraft configuration, with such a staggered and swept boxwing, a wide-body fuselage and twin vertical tails, has been recently referred to as the Prandtl plane. And this is from the name of one of the fathers of modern aerodynamics, Ludwig Prandtl, who was the first one to discover the important properties of the boxwing, and in 1924 he called it the best wing system. Now, why did he call it like that? Because no matter what the particular shape or design of the boxwing achieves the minimum induced drag for a given wingspan and weight. Now, you may already know that induced drag is related to the creation of lift, and as such, it is associated with the creation of vortices behind the wing. Now, the intensity of these vortices can be reduced by either increasing the wingspan, as in the case of a thrust-braced wing, or by introducing winglets, as in the case of many existing aircraft already in the real world. In the case of the Prandtl plane instead, you can imagine that the rear wing acts as a huge winglet for the front wing, and also vice versa. In this way, maybe you can convince yourself that the intensity of the vortices behind the wing is minimum, and so is also induced drag. Now, how can we put this property to good use? Consider the two most numerous aircraft configurations currently in service: the Airbus A320 family and the Boeing 737 family. They are both characterized by a wingspan of approximately 36 meters and can carry about 150 passengers in a two-class cabin layout. Now, if you were to design an airplane based on the boxwing concept, but with the same wingspan, you would first of all retain the possibility to use the same ground infrastructure already available in all airports of the world. And I'm talking about passenger gates, hangars, or maintenance facilities, for example. Note that this would not be true for the truss-braced wing, which needs a larger wingspan to achieve improvements in aerodynamic efficiency, and is quite a relevant aspect in our modern world, where population and travel demand keep growing and growing, while space for new facilities becomes less and less available. Secondly, thanks to the improved aerodynamic efficiency, the boxwing would make it possible to either transport the same weight of the A320 or B737 with less drag, and hence consuming less fuel, or would make it possible to carry more weight with the same drag of the A320 and B737, hence being able to transport more passengers per flight, and overall needing less flights from point to point. From some preliminary studies comparing the flight performance of a reference aircraft resembling the Airbus A320, also equipped with new generation engines, and a frontal plane with a 36-meter wingspan, it can be seen that these scenarios are actually not so unrealistic. For various short and medium mission ranges, from 2,000 kilometers to about 6,000 kilometers, and for two different flight strategies, it can be seen that the A320 consumes about 17.5 grams of fuel per passenger per kilometer, with 150 passengers, while the frontal plane consumes between 14.5 and 16.5 grams of fuel per passenger per kilometer, with 308 passengers. So, in other words, the frontal plane uses less fuel per passenger to move more passengers on a short and medium range route, and hence can be defined as a more efficient means of transportation. Another aspect to be considered stems from the fact that the geometry of the staggered boxwing makes it possible to install multiple redundant control surfaces all over the two main wings. By coordinating the deflection of these control surfaces, it is then possible to perform any maneuver in infinite different ways, and also to choose an optimal way to achieve some desired performance. For example, control surfaces could be coordinated to achieve direct lift control, which makes it possible to change the aircraft lift without any change in the angle of attack. This could be especially useful to make the aircraft feel more precise and agile to the pilot commands, and also to make it react faster to external disturbances. Direct lift control would reduce the vibrational load felt by passengers and structures in a turbulent airfield, for example, resulting in more comfort on board and an overall safer flight. Also, it could allow precise control over the flight path angle during descent and landing phases, allowing for steeper continuous descents and lowering the noise footprint of landings close to urban areas. In summary, what have we learned in this video? The boxwing is a closed wing system which achieves minimum induced drag regardless of its particular shape and design. By integrating the boxwing geometry with a wide-body fuselage, the frontal plane could manage to transport approximately double the number of passengers of the A320 and B737 while consuming less fuel per passenger and using the same ground infrastructure. Finally, redundant control surfaces on both wings of a staggered boxwing can be coordinated to achieve direct lift control, which results in more comfort and safety in flight and in a lower noise footprint during descent and landing. Of course, there are still many challenges to be faced for the boxwing and the frontal plane, but research is ongoing to explore this novel configuration and its practical operation as a potential solution towards more sustainable aviation.